All right, so the nice thing about technology is we can use it to fit the data to an equation. Now, as always, we're going to have to consider the behavior suggested by a scatter plot before using that technology to find the equation, though, because sometimes, if our data says it's going to go up and up and up, well, it might come back down, but if they stop and we don't have data past that point, then we have to kind of think about does it actually reach a maximum or a minimum if it's going the other direction? And so we have to think about, does the data exhibit those obvious maximum minimum points? They're easily identified in the quadratic sets because that's where it reaches that. And what could be happening is we don't have a knowledge of what goes beyond. Maybe we know that as I don't know, time goes on, we're going to increase our pay. Well, that's just going to keep going up. So that wouldn't come back down because we're not going to, as time go on, we're not going to decrease our pay. If we keep at the same job, it should keep increasing. And so it's going to go up like that. So it's going to be more of a log plot. But we don't know that. And so a scatter plot on one side of a parabola could either be a log plot or an exponential. So like I said, up to that point, it could be either one. We don't know for sure. So we have to think about that trend beyond to figure out what's going to define this as a quadratic or a log or an exponential maybe. So that's kind of the key thing is we have to think about that. Now, some preliminary steps in choosing a model. So I just basically lifted this straight from the book because it's really kind of good. So in real life, data doesn't come to us with instructions attached to tell us what kind of functions to use as a possible model. So what we have to do is first consider the underlying processes that may be influencing the relationships between our input and output and what end behavior may be exhibited. So again, we're going to look at the curvature. So we're going to look at a scatter plot basically. Now, if the scatter plot suggests a function that is curved but has no obvious change in concavity, try the quadratic and exponential or log model based on the behavior. Now, include your end behavior and look out how it affects that scatter plot. Note if the input values are equally spaced, it might be helpful to look at first differences, percentage changes, and or second differences. And we'll talk about that in a little bit, the first and second differences. Okay, so if they're equally spaced, that's kind of a nice thing to do. Now, we can look at the fit of the possible equations too. So after step one, there should be at most two choices for a possible model. So what we're going to do is we're going to compute these equations and graph them on the scatter plot of the data. And then when that comes closest to the most points, but doesn't necessarily go through all of them, is normally the better model to choose. Now, what we want to do is consider that maybe two equally good models for a particular set of data. And in that case, we choose one and we go with it. And we say that's the model we're going to use and that's okay because sometimes two models will fit a data very well, and so we just have to choose one and say that's what we're going to use. All right, so this second differences thing. So it's a method for deciding whether a quadratic function fits data using second differences. So the differences is of the first differences, which is from our original output. So we have our output, okay, and those are the basically your y values. And what we do is we take a difference between the first two, and we get a value. We take a difference between the second two, and we get a value. We take a second, and third, and fourth, and so on, and we get all those values. And that's called the first difference. Now, if we want it to be quadratic, what we have to do is go ahead and take a second difference. And so then we take a difference between the first two that are left, and we get a value. And then the next two, the next two, and the next two. And if these are basically constant. There's very close to no change here. Negative 0.3, negative 0.3, negative 0.2, negative 0.2. That would be, I would consider something we would use to look at the quadratic. That would be an ideal one there. Okay, and sometimes that's where we have to get to if we're fitting it and we're not sure. We do this first difference, second difference, and then we get our output to see what it looks like here. All right, so I'm going to pause there and then we're going to go to actual problems next.